Okay, welcome back. So this is part 2 out of 2 for making sense of polarization. It's a tutorial on understanding polarization effect in Raman scattering. So if you have not seen the part 1, maybe you may want to see the part 1. In part 1, what we did is to understand what's happening in geometrically and the fact from a mathematical standpoint that you can see a Raman scattering as a machine that rotate and rescale a vector gi. So the machine is described mathematically by the tensor alpha. Now, the intensity of the Raman scattering will be proportional to the square of the dot product, so the projection of this effect of the machine on the incoming light on so the product with GS. So we are going to now in this screencast now see how we can understand this graphically, which actually makes it so easy to understand what's happening. And then I will show you how, thanks to that, we can understand a setup that's a little bit more complicated. So remember what we are working on. Graphically, we have a sample. We shine light to it with polarization GI, incoming light. And then we are looking at what's happening in the scattered light for polarization GS. So graphically, we suppose that GI and GS are going to be normalized vector, which they are. We can actually look at them on the unitary circle. And the unitary circle is like this. We have a vector GI, which is along theta, so the polarization, and we have GS, which is along phi. So these are, of course, generalized vectors. Very often we use GI or GS along a specific direction, like 1, 0, 0 or 0, 1, 0. But what I'm going to explain to you works for any angle. And so we are trying to see the effect on how we calculate this intensity here. Now, it's actually pretty simple, because when you think about it, this is the main point of the entire remainder of the screencast. So this is now. Alpha rotate and rescale GI. So it's going to create, after the application of the Raman scattering, is going to move the vector G into the blue one. The blue vector is going to be rotated, but also is going to be not as long, simply because it can be longer, right? You cannot create a longer polarization vector after some scattering, so it's just going to be smaller, like here. So this is what you have. The effect is this. So this is the step number 1, right? Step number 1 is that the effect of alpha on GI is to rescale and rotate the vector. Okay, let's go to the second step. So this is where we are, right? We start with an incoming polarization and then scattered polarization. So GI is this vector here. So the equation on the bottom left is the equation we use for the intensity. Now, the Raman scattering is going to rotate and rescale the vector, as I said many times already. So it's going to do this. This is essentially mathematically the tensor R, Raman tensor applied to cos theta, sin theta 0. And then finally, we are looking at the scattered light. And this is a dot product between cosine phi, sin phi 0, and the result of the scattering. In other words, the dot product is a projection of G on GS. And so what's very interesting is now the intensity of the Raman intensity that we calculate for those two polarization is going to be proportional to that amplitude, which is, of course, that length right there. Okay, so the length is actually the amplitude, the intensity being the square. So this is the most important slide. If you understand this, you're going to understand the rest of of everything, and you see how beautiful this is going to be. So let's try to make sure. Let's illustrate this on a couple of examples. Let's go back to our MOS2 mode, and we're going to look at the A mode, and we are going to look perpendicular, so really cross polarization, as I called it before. So basically GI and GS between orthogonal to one another. Now, what's interesting is that the A mode, as we mentioned in the previous screencast, is diagonal. So as being diagonal means that it is not going to rotate the vector, actually. It's only going to rescale it. So after Raman scattering, the vector is actually along GI. In this case, of course, that vector is also orthogonal to GS. So the dot product between the two is going to be 0. The projection of G on GS, when they are orthogonal, is always 0. So the A mode in the cross polarization is going to, the amplitude is always 0. Okay? Now, let's have a look in the parallel polarization. In that case, GI and GS are parallel to one another. So here I couldn't plot GS really because it's on top of GI. That's why I noted it that way. Now the Raman scattering again does not rotate the vector in this case because it's a diagonal tensor, but it's rescale it. So it gives this like this. And of course, in parallel polarization, we are actually, in this case, calculating the projection of G on GS, which of course is a constant, since G always follows GS, and there is no theta dependence. And in fact, the length is going to be B. Isn't that nice? Let's go one step further and look at the E1 mode, so one of the two E modes. We're going to suppose again that my two polarization vector at an arbitrary angle theta, but it's going to be in cross polarization. So basically there is a 90 degrees angle, so therefore the theta, as you can see, can be found easily between so it's an arbitrary GI, but the GS is orthogonal to it, so the angle between with the x-axis or the angle with y-axis are the same. Now what's interesting in this case is a little bit more interesting than the A mode, because the tensor is actually doing this. Now, it's not diagonal, so there is a rotation. So suppose that GI is cos theta sine theta 0. Now we see directly that the effect of this is to basically swap the sine theta and cos sine theta, and then rescale by a factor A. So you can actually plot this, swapping theta, so swapping the sine by the cosine and cosine by sine can actually be done like this. And in fact, geometrically, the fact that you are doing this, replacing cosine by sine and sine by cosine, is basically saying that there is an angle theta right there. So it may be a good place to stop the screencast and convince you of this. It's a fairly simple geometric effect. Now the blue arrow is a little bit shorter because it is rescaled by A. So basically it lives on this circle, which is no longer a unit circle. It's a circle of radius A. Now, how do we get the intensity? Well, get the intensity by projecting that vector, the blue vector, on GS. So like this. And I actually plot it back on the left-hand side. And we see that that triangle that we are working with is a triangle of angle 2 theta, for obvious reason if you followed. So basically that length there, which is dark black line, is going to give you the amplitude of the Raman scattering along that vector. And you see that that vector, that intensity is never 0 unless theta is equal to pi over 4. And in fact, and we will see that in a minute, the intensity of the Raman intensity for this A1 mode is a function of 2 theta, not a function of theta. So unless theta equal pi over 4, in which case the blue vector will be perpendicular to the green vector, that the amplitude is never 0. Okay? I invite you to convince yourself and do this exercise for the E2 mode. I didn't do it in this screencast, but I trust you can do it. However, I've gone in much detail in the next part of this presentation, which is the most specific setup, and it's going to show you the strength, the power of using this graphical interpretation to explain experimental setup. And the setup we're interested in is the one that's described here. It's a fairly typical setup, in fact comes in commercial Raman scatterers. And I actually got this picture from this paper, which is a paper on MOS2. It's an interesting paper. Let's try to explain what's happening here. So this experiment, we have a laser. The laser goes to the sample. There is a Raman scattering. and the light comes back and being analyzed in the at the CCD part. But in between, we have some stuff happening. First of all, we have a polarizer. Second, we have a half wave plate, which is really the focus on this part of the setup. And finally, we have the analyzer. So let's try to look at those three and see how we can interpret this mathematically and graphically. The polarizer ensures that light is linearly polarized. So basically, when we say linearly polarized, we just say that the electric field, which is the direction of the polarization, this is the definition, is always in the plane wave, like in the plane, lives on a plane and is linearly polarized. So it's not it doesn't go on a circle, which would be a circular polarization. The half wave plate is actually an interesting animal that I'm going to talk more about in the next slide. But for now, if you ask somebody what does the half wave plate does, it rotates light. So it rotates light by a certain angle, and then you can basically pick the angle. Well, in practice, you do not pick the angle in a continuous way, but it's fine. It doesn't matter. For our purpose, the half wave plate rotates light. When we say rotates light, we really mean rotates the polarization of light. And finally, the analyzer basically picks a direction of the measured polarization. So this is where we pick the direction for GS, for example, so the scattered polarization. Now, one thing that we have to, there is one point that we need to understand very well if we want to move further with this, is the half wave plate. And I'm not going to give you an introduction to the half wave plate in too details. I'm just going to tell you what it does. The thing about the half wave plate is that it does not just rotate the polarization. What it also does is introducing a phase shift along the principal axis. Now you can ask and I'm going to tell you what really means, and we're going to see that in detail. Now, why doesn't it just rotate? But remember, I mean, I am a theoretician. I'm a computational physicist. I would love to have something simpler, but the reality is that you need to do experiment, and the experimental setup to rotate a polarization like using a half wave plate also does something else, which is introducing a phase shift. It's because it is rooted on a physical phenomena. So you can't just pick whatever you like because a theorist would prefer it. It's actually done experimentally. Now, let me try to explain what it does. So basically what it does, the half wave plate, first, there is a principal axis because it's all based on optics. And there is the introduction of a pi phase shift for the y component, let's say. Suppose the y axis is the principal axis. There will be a phase shift along that direction, and then a rotation. This is how it works. So the phase shift means that of 180 means that the y axis is basically inverted, right? A pi shift is basically a rotation of 180, which is basically inverting it. So the first thing it does is actually inverting things. And we suppose that this lives in the xy plane. That's why we have 0 on the z. Now, it does that. The pi shift is to invert the y-axis, which is this tensor is exactly what it does. This matrix is what it does. And of course, followed by a rotation. And of course, as you know, in linear algebra, we read from the right what applies first and what second. So this rotation there is a rotation matrix, is a rotation matrix that you would see geometrically. But the half wave plate actually does those two things. Of course, you can calculate this very easily, and you obtain this matrix. And this is really the effect of the half wave plate. It is not just to rotate, it's to do a little bit more. And in optics, it is a well-known matrix. It's called the Jones matrix. So I'd like to really insist on the fact that matrix, the Jones matrix, even though it represents the half wave plate, it is not a rotation matrix. From a mathematical perspective. In fact, if you calculate the determinant, you find the determinant is -1. And as we know, the determinant of a rotation is 1, right? So this is not a rotation, but it's fine. We are going to see how we can take that into account in a graphical approach. So it's very important to know this. So I like to remind you the pi shift comes from the fact that you flip the polarization. You have to flip the y-axis in due to how the experiment works. I like to tell you two things here. The first one is that for this to work, the entering light must be linearly polarized. It's the reason why you will always see a polarizer in front of the half-wave plate. You must have a polarizer in front of it, because if light is not linear polarized, I don't know what's coming out of this. Second, in reality, when you do the math correctly, but of course the screencast is not about the Jones matrix, you actually have an additional I, phase I, which is a prefactor for the whole thing. But it doesn't really matter, because that phase is an overall phase that does not affect our intensity. So it's not a big deal, but strictly speaking, there should be a factor I in front of the Jones matrix if we want to do that, but it does not really matter to us as we calculate the intensities, which is the square of the modulus. Now let's see what it means to make sure that we put all this in perspective. Let's remember the half-wave plate first invert the signal on the y-axis, and second rotate. That's what it does. Let's see what happens on our graphical interpretation. Suppose you have a rotation by phi. Let's try to see, for example, if you start with 1, 0, 0. So this is the red arrow. I hope you see it. GI is on the red arrow. The first thing is to invert the y component. Well, in this case, there is no y component. So the effect of the halfway plate is just to rotate by angle phi. That's what it does. Nice. Now, suppose that you start from 0, 1, 0. This is again the red arrow. Now here you do not have just a rotation. You first invert along x, so this is the dotted arrow, and second, you rotate by phi. So you see the effect of the half-wave plate is a little different on GI on the second case, on the first case. And you can even convince you in a general case, if you start with GI a certain arbitrary angle theta, the first effect is to invert the component along y, giving the dotted arrow, and second, to rotate by an angle phi. In this last example, I use a phi that's a bit bigger so that it's clear in the picture, but that's fine. It doesn't matter, phi is arbitrary. Again, this is a good place to stop and convince yourself that you understood this. And this, of course, the beauty of YouTube videos is that you can go back 15 seconds, or if I go too slow, you can even go faster. That's up to you. Now, let's go back to the experimental setup. And this is really what can be a little bit challenging sometimes when you're not used to doing this. There are two things here. The problem is the light comes in, goes through the half-wave plate, gets Raman scattered by the sample, and goes back through the half-wave plate. So you really have two half-wave plates. How do we deal with this? Well, let's do it. And I think this is what I find particularly nice with this geometrical interpretation, the graphical interpretation. So let's use our nice unit circle. And we are going to follow the journey of light as it goes through from the laser to the CD camera. First of all, we start with a linearly polarized light in orange, which are going to pick as 1, 0, 0, for example, right? And this is going to be at this orange box. So the box is actually going to move to show you where we are. First of all, this vector is going to come to the half-wave plate. Well, the nice thing about the half-wave plate for the 1, 0, 0, there is no y component, so there is no inversion. So no worries, the half-wave plate is really to rotate by theta. So GI after the half-wave plate. This is the polarization that's going to hit the sample. So this is this box right here. Now, this vector, this polarization hits the sample, and as you remember, the Raman machine is nothing else than a tensor that rotates and rescale the polarization. So after this, that's going to be the other box. So you see on the other way is to create to generate this vector that's rotated and rescaled. So we are going to do just put that on a constant radius domain, so a circle, so that we know what we do. Now, this particular light now is going to go through the half-wave plate. So what does it do? Well, here the problem is this vector has a y component. So in order to calculate the effect of the half-wave plate on this polarization, we have first to apply the inversion, the pi phase shift, so it's going to the dotted line, and then rotate this vector by theta to get the green vector after the half-wave plate, which is basically the vector we have here. And the final step is to project that green arrow on the angle of the analyzer. Here I've not done it because we don't know what the GS is, but the projection of this vector on GS will give you the amplitude of the Raman scattering. So again, this is one of the places where you could go back and understand what we are doing, but we actually interpret the interpretation of the entire experiment through this graphic. I'm going to show it to explain that to you in 3 cases. So maybe before you rewind the tape, as we used to say, instead maybe look at the explanation I'm going to provide you. Hopefully that's going to be good. Now let's look at the A mode. The half-wave plate is going to be at theta again, just like before. Here it's beta over 2 because it's the original picture, but imagine it's theta. We start from 1, 0, 0. Effect of the half-wave plate is to go here. Now, this light hits the sample, but the particular Raman machine in this case corresponds to the A mode, which is a diagonal tensor. So in other words, the effect of the tensor on GI is just a vector along, which is collinear, which obviously since the tensor is diagonal. And then after that, you go again through the half-wave plate. The half-wave plate is first to invert and then to rotate by the same angle, right? So you see that in this case, the fact that we have inverted and rotated gives me a vector that's along the cosine, so the x-axis. Okay? Make sense? If we measure the Raman scattering along this axis, so along 1, 0, 0, we find the length of the green vector. So in other words, B. Now, if we were to measure this along the y-axis, so on 0, 1, 0, so GS equals 0, 1, 0, in this case, the projection of the green vector on 0, 1, 0 is 0. In this case, we don't see nothing. We don't see anything. So you see, the first case would be a parallel configuration, since the initial light is the same direction as the final. The initial polarization is the same as the final polarization, while the other one would be a cross polarization. Okay? Now let's even do something better, and this is the most complete example I'm going to show you now. Now, again, I'm going to give you a little, just a warning. I'm going to first talk to you without going in the detail of the angles, and then I will replay this with the angle. So pay attention on the principle, and then we will look quantitative in a second. So the E mode is a bit more interesting. This is the vector. This is the tensor, sorry. So we start from 1, 0, 0. The effect of the half-wave plate is to rotate this. Now the effect of the Raman machine is to apply this tensor. And we see here that the effect of this is to swap the x and y component, right? This is what this is. And then rescale by A. So we swap the sine and cosine. That's basically what this tensor is. So we end up with a G vector, so a vector after Raman scattering here, which is not as long. It has a length of A and lives on this circle. Okay? Now, this light has to go through the half-wave plate again in our particular setup. First, we have a phase shift. Then we have a rotation of theta. So we end up with this green vector after half-wave plate. Now, if we measure this light, the length of this vector projected on 1, 0, 0, so the parallel configuration, we find a square sine square 2 theta. So you already see it's a sine because it's the length of this black arrow, which is of course on the sine. We are going to see why it's 2 theta in a second. And if we measure along 0, 1, 0, we find the orange, the length of the orange, which is a cosine. It's the projection. The projection here is the definition of cosine. Now let's go back to this with now adding the angles to it, just so that you see, even though it looks like a messy picture, it's actually not. It's actually very easy to do if you do it systematically. So we start here. This is my starting polarization right after the polarizer. The effect of the half-wave plate on this incoming light is to do this at an angle theta. The effect of Raman is to rotate here by swapping the x and y component and then rescaling by a. And of course, if we do that, the angle there is also theta. This lives on this circle of constant radius a. Now, the effect of the half-wave plate on that particular light is to first invert the y component, which is of course at theta, and then to rotate by another theta, right? This is what we've discussed. So there is another theta right here. So now you see, very simply, that you have 2 theta, an angle of 2 theta. And this is why this particular length here is going to be related to sines, actually it's minus a sine 2 theta, but we take the square for the intensity. And this one here will be related to cosine. Isn't that beautiful? I mean, you understand, not only you understand qualitatively, but you can also understand quantitatively if you put your angles right here. Now, the final example is the E2 mode, which is actually easier because the E2 mode, the effect of the E2 mode is it's also a diagonal tensor, sorry. You start from this vector, you go through the half-wave plate, so you rotate by theta. The effect of the Raman scattering is to in fact swap the y-axis. This is the minus, and then at of a size a. So this is after the Raman scattering. Now this light has to go through the half-wave plate again. When it goes through the half-wave plate, it goes there, right? You see, I hope you saw the arrow. It's there because it's inverting again the y component, and then it rotates by theta, right? This is the half-wave plate on the scattered light coming from the Raman, from the sample. And then you measure this. While you measure the length of the green arrow, depending on the axis that you pick, it's your GS. So you can pick it, for example, along 1, 0, 0. That's going to be this length, which I didn't mark on the plot, but the length of the projection of the green arrow on the cosine axis. And again, you see the 2 theta, so it's cosine 2 theta, and then the intensity is the square. Or you can have the length here if you measure along the 0, 1, 0. So this is all there is to it. And if you understand all this, you can apply this to any material, any tensor, any configuration you want. All that matters is to follow the arrows. So I hope this was a useful series of screencasts. I really like to thank you. If you like this style of presenting things, I invite you to look at my many other presentations in different field of physics and material physics in particular. Thank you very much.